Okay, so it is 1:45, so we can start, I hope. Today we are going to talk about trees, an example of a tree you can see on the screen, and we will process them in some basic way. We will create some trees, and then we will just look into the trees and see what is inside them. And we will do a little bit of backtracking at the end of the lesson. So without much ado, I jump directly into the topics. So, a tree. What is a tree? A tree is a system of, as you can see, small dots or points, or typically you call them nodes. And if you want to be really posh, then you call them vertex. Graph theorists call them vertices, vertex-vertices. So those are nodes or vertices, but node is generally shorter, so typically you will incline to call these things nodes. What is inside node is not important. We typically do not assume that they have any special internal structure. Sometimes we store some values in nodes, relatively often. But that's all. So it might be a storage for some data. And then there are the edges, which are connections between pair of nodes. You can think of some pair of nodes, and when you connect them by the edge, then you have a connection. By the edge, of course. Some nodes are not connected, some are connected. Typically and very often, we consider between any two nodes at most one edge. We do not create many edges between two given nodes. Typically, it is not it's not important, or it is not needed. There might be some situation when it is important, but we will not meet them. So you can think always between two nodes, at most one edge. And now comes important distinction, which says, okay, so nodes and edges, what is important? What is important that if you want to have a tree, you should not have any cycle or any loop inside that tree. So the example on the right side is not a tree, and there are some tree properties here at the bottom which tell you what to expect from your ordinary tree. It is connected, so it is always made of only of one part, which means that when you start in some node, then you can walk along the edges and come to any other node you wish. So that means it is there is a path, a sequence of edges between any two nodes. That means it's connected. There is exactly one path between any of its two nodes. You cannot, when you start walking, for example, here in example D, from the left to the right, there is only one possibility how to get there. Because when talking about paths, we exclude possibility of going there and back along one edge. So a path is a sequence of edges which do not repeat. You have to move forward and forward and forward until you arrive to your destination. So there is exactly one path, which, as you can see, is not true in this rightmost example. If you want to get from the very bottom to the very top on the right, when you arrive to the central part, you can go either directly on the right side, or you can make a little detour and then come back and again move upside. So then in such case, when there are more possibilities how to get from one node to another, it's not a tree. Now, removing any edge results in tree divided into separate parts. As you can see in all examples here, whenever you would remove any edge, the tree will fall apart into two pieces. Excuse me. And important thing is that the number of edges is comparable to the number of nodes, no matter how the tree looks like. You can have any example you can think of. There is an example of a tree, 2, 4, 6, 7 nodes, 2, 4, 6, 2, 4, 6 edges, which should be more or less obvious because any tree is built in such a way that you can start with a simple node, and then building a tree, what you do, you create a new node and connect it to your previously existing tree. So that means you add one node and one edge. And if you continue, so again you create one node and one edge. Again you create one node and one edge, and you are connecting those to the existing tree. So always you start with one node, and then you each time create one node and one edge to create your tree. So there is always one more node than the edges. So it is important to know, and what is even more important to know that it is more or less the same number. The plus minus one in most computational applications do not matter. Okay, so trees are such things, and we will use them for various purposes throughout the whole semester, and also later, because anytime you come anywhere into computer science, you typically meet some kind of trees. So, so those are examples of trees, and now we'll make it a little bit more precise. Everything what's going on in the tree we can say, and we can choose, and again often we will choose one particular node in the tree, and we will call it a root. That would be the most important node in the tree, because well typically it will be an access point to the whole structure. What is a root? Root is just one selected node. No one prescribes you in advance if you are given a general tree, which one should be the root. You can choose it, but typically people, when they bring you a tree, they also often bring you also the root of that tree. So, on the left side, you can see usual tree. Somebody has chosen the root, and then the picture, which is on the left side, can be redrawn in the fashion which is depicted on the right side. What is important that the scheme, the system of connection, is exactly the same on the left side and on the right side. When you start in a root, its neighbors are A, B, and C, and you can see here that the root is connected to A, B, and C. And in their turns, the other nodes are connected to the same nodes on the left side as on the right side. C is then connected to D, C is then connected to D. D is connected to F and D, F and D. And the rest is analogous. Pardon. So now what does this mean? This means that now we can have some measurements in the tree. Especially, we can think about the distance of each node to the root. How many steps, how many edges have you to traverse to get to the root? So for G it is 1, 2, 3, 4. For K it is 1, 2, 3. For C it is only 1. For R it is exactly 0. Make 0 when we are in R. You make 0 steps. You are in R. So you can have something like kind of levels, for example, the nodes which have the same distance to the root. And now, of course, when they are in this way organized, then we can distinguish always a child and a parent of a node. So if you take any node and then look downwards to the next level, you can see the children of that particular node, those which are immediately connected by one edge to a node. M, J, I, N are all connected to A, and they are children of A. On the other hand, A is a parent for each of M, J, I, N. Root is not, root would be a grandparent, and N would be a grandchild of R, but those terms are not used that often, so typically you speak about child and parent. Also, you can use some predecessor, successor, maybe son or daughter, but the most typical ones are these. So we have got some terminology. Let's go to do some measurement. Now what's this? This is the same tree as before, and now the levels are exactly the same as before, and just are labeled by their particular so-called depth. That is the distance from the node to the root. So each node in a tree suddenly has some particular depth, of course, related to the root. The depth of the whole tree is the biggest depth which is in the whole tree. So the tree depth is an obvious concept as well. Now, all right, so you might say, well, so what? And I will tell you that the definitions will continue for a while. There are more properties of a tree which we have to be able to talk about. So, binary rooted tree. The tree is rooted. Typically, we draw the rooted tree with a root. Typically, we draw the root at the top, and then all the branches of the tree are dangling down, and that's it. Now, what is important that the tree is typically, when we draw it in this shape, we consider it to be rooted. Root is at the top. Now, this one is a binary tree, and binary tree, exactly what it is, each node has 0 or 1 or 2 children. So, if you draw something like this, this is a binary tree because each node has either 2, either 1, either 0 children. Each node in each rooted tree has always exactly 1 parent, except for the root which has no parent at all. So those are binary trees. I will give you another example of a binary tree. For example, something like this is a binary tree, and when you move from the root downwards, you either have to move forward or there are at most 2 children on your path. Okay, of course, then we can talk also about subtrees, as they talk here at the bottom, and that's an important feature of a rooted tree, that when you take any node, you choose any node in that tree, and if you forget about everything which belongs, which is above that node, and consider only the its children and children of their children and grandchildren and so forth and so forth. If you consider this part and forget the rest, it is also a tree. And it happens anytime. You choose any node there, take this, and this is a tree as well. And the node is a root of the subtree, which is rooted in that particular node, for example, y. So there is node y, and there is a subtree rooted in node y. So that means that whenever we have one tree, we also have a zillions of other smaller subtrees, which are trees as well. And what is important that we distinguish left and right subtree, as they show here in the picture. Left and right, the concept should be obvious. Left, the part of the tree which is on the left and which is on the right below that node. So those are binary trees. So with some examples. Now there exist regular binary trees which say, well, what must happen? Regular, that any time you come to a node, there is always a fork to the two children, or you stop. So the tree which is here on the blackboard is a regular binary tree. So I can say this is regular. And if you draw something like this is regular, and this is not a regular tree because there is a node which has only one child. It's not regular. What is the balanced tree? Balanced tree is this beast. I think we will see it more times today and also later, but the terminology is not that completely clear. Typically, you talk about balanced tree when it looks more or less maybe with small changes like a balanced tree. Like a balanced tree. So this is obviously a balanced tree. And when you, for example, add here and there a few small nodes and you look at it, well, it looks more or less like balanced. Typically, you would tend to call this thing a balanced tree as well. Balanced because if you forget small details, you get a balanced tree. To distinguish the picture which is here on the right from the picture which is on the screen, typically we would call that one on the screen perfectly balanced. If you say something is perfectly balanced, that it has to look like that one. All leaves, that mean all nodes without children, should be sitting in the same depth. If they sit exactly in the same depth, then you have a perfectly balanced tree. So, okay, the depth, and all right, so what's the fuss about? What we see here on the next picture is that they try to communicate to us the fact that the number of nodes in particular depths in a regular binary and balanced tree grows very quickly. So there is only one node in the depth 0, that's the root, and then you can see that each next level contains twice as many nodes as the previous level. So here they show it to you. So for example, when the depth is 4, they say then the number of nodes in that depth, this in that depth, is equal, they say, 2 to the power of 4, which is 16. If you go to depth 8, the number of nodes is not 2 times 16, or it is 4 times 16. It is 2 to the power of 8, which is 256. So that would probably not fit on the slide. If you move another 4 levels down, if the depth is 12, then the number of nodes is 2 to the 12, which is about 4,000. I think it's 4,096. Okay, 4,096 to be up. If you get to depth 16, and that is 2 to the 16, and I do not exactly remember the value, so it is something over 65,000. There are typically always people in the audience which do know exactly what is this, but that's not important at the moment. So in the depth equal to 16, we have 65,000 nodes. So just imagine here up on the screen we have first four levels. So only 4 times lower. Take this vertical distance and multiply it by 4. Put it for the second time, third time, and fourth time. So more or less at the upper border of the blackboard, we would have, if we continue with this picture downwards, we would have 65,000 nodes. If you go to the to level 20, you have 2 to 20, which is about 1 million. 1 million, and take that, it's just about that size. So continuing the binary tree from the top to this position, level 20, we would have 1 million, and here at the bottom of the blackboard we would have how many, 16 millions or something. Something like that. So the number of nodes, what is important, the number of nodes as you go down grows very quickly, and therefore they tell you that the number of nodes grows exponentially as you are getting lower and lower, and also when you turn it around, the depth is proportional to the binary logarithm of number of nodes, as you can obviously see from this table. Binary logarithm of 65,000 is about 16. So when they have a big balanced regular binary tree and with some number of nodes, you can easily say, the depth is probably a binary logarithm. So, for example, there are many examples here. So, if you've got, for example, how many? It is very representative. Let's say you have 100 nodes. So what does that mean? That you take binary logarithm of 100, which is about 6 point something. I have no idea how much it's 6 point something. It's 6.5. Maybe 6.6, I don't know, something about this much. So you know, that is 6.6. So the depth of the tree would be a little bit more than this, about 7. 0 and 2 to the power of 7. No, it would be 6. There would be seven levels in the tree, including the root, and there will be 6 levels, isn't it? That is 16. 5 would correspond to 32. 6 would correspond to 64. And you cannot put there down all 64 because you would arrive in total to 127 27 nodes. So that's about it. Calculations with a tree. Now another preparation part before we start processing the trees is the implementation. Typically, we will store, when we will use trees for searching and for storing data and such stuff, we will typically have some trees which will be made by the nodes and connections between them. And the node then typically would look like a key, which is the information which you want to have stored in that node, there, but I don't know, we will come to that later. Just some additional information you want to store there. Then there might be a reference to the parent, as you can see described by these arrows, and there are references to the left and the right children. So there you can see when you create a new node and initialize it, you say that left, right, and parent, they do not exist when you just create a node and it is not yet in the tree. And then you just into the key, you store whatever value they give you, like a parameter. Sometimes parent might be omitted or not used at all. Sometimes you don't need, when you process the tree, you don't need a reference to your parent. So in that case, you can have something like this, just with the parent omitted, and they might not be important down there. So it is just easy representation. If I remember correctly, we have some codes, some Python codes on the web page with our lectures. I did not. Sorry, that's not easy to manipulate these machines. Where you can go and check yourself. For example, typical implementation. Try to open it. Will they be able to open it? They will be, but they cannot open such. Wow. System Windows cannot open that file. For example, in Word, fine. Try WordPad. There is no programmers. It's not a programmer's programming environment. It's a WordPad. No one knows what it is. But you can see that there is a class node which with defined constructor which creates the node, and then there are some methods which manipulate the nodes and the binary tree as a whole. So I hope I can minimize this for a moment. So those codes are meant to your own studies. Sorry, or you might consult them during our seminars, or maybe when you create your own homework. So I just mentioned we have them available, these codes. So this part just wants to show you that it's an easy stuff to have a tree, and after some time I will be able to maximize the window again. Having defined a node, we can go and build a random binary tree just to be able to do some experiments. The binary tree looks. How do we construct it? First of all, what is the result? The result is something like this. At the top is a schematic picture. At the bottom is more code-related picture, which reminds you that there is some information, so-called key, in each of the nodes, and each node contains references to its left and right subtree. If the right subtree, if one of the subtrees does not exist, then the reference, of course, is none in Python, null or nil in other languages. Simply, it's an empty. It's a pointer which points nowhere. So that's the result of the function which I am about to present. So how do you build a random binary tree? For the first time, we meet here this recursion stuff. That is the method when you are processing some data, you do such thing that you take one piece of the data. Typically, you take one node when processing a tree, process it, and then continue to the left and to the right subtree, and there you do structurally the same thing. So you don't have to repeat it. You just call the same function you are working with. So when they are creating a random tree, they create a new node. They create a new node, as you can see here in the middle. It's a node which gets, it's a method which gets some numerical parameter, and that numerical parameter is some random number, randomly chosen from range from 10 to 100. I think a random range with parameter 90 gives you something between 0 and 90, and when you add to it 10, you got something between 10 and and 100. So here they create just a new node according exactly to the this init constructor. So there is a node, and what we do now next is, when that node exists, we put into its left part and the right part, we put what? Another random tree. So effectively what happens that you have your node. Your node is here, you put there some randomly chosen value, like 71, for example, and then what you do, instead of thinking, how do we build the rest of this big tree, you say, oh, no, we don't do it. We just use the same function, ask the same function, a random tree, which is exactly this one, to create a complete tree. It is capable of creating a complete tree exactly by the same method, that when it comes to the left subtree of the node, there it goes and creates some random value there, 56, for example. That does not matter, and it contains left and right children, and there again happens the call to the left and to the right subtree. So again, these nodes will be created. And so forth, and of course the same stuff happens on the right side. And the nodes are being created one after another. And of course, because this is a call to the same function, you have to stop sometimes. Otherwise, you will have infinite process which will be generating new and new and new nodes. and will never stop. So how do you stop it? Well, anytime a function is called, you can see that it has some particular parameter, which is called depth in this case. And what you do, when you are going to create your one node, before you do that, you say, aha, and what is the depth? Which they gave us as a parameter. If the depth is small, if it is 0 or smaller, then we say, no, we don't do anything, we stop. So if you start, for example, with the depth equal, in this case, 1 to 0, 1, 2, 1, 2. So when you come to the first node you have to create, the value of the parameter would be 2, which of course will not pass this test. So you will create a new node, and then you will try to build a random tree, call the function itself with a parameter smaller by 1. So when they are creating nodes in the next level, then the depth will be only 1. And so forth. So maybe we should start with depth 3. That is, depth is less or equal than 0. So we have to start with depth equal to 3, isn't it? If we want to create this stuff, depth equals to 3, depth equals to 2, depth equals to 1, which might be, yeah, let it be. So, and it is not depth of the node in the tree, it is just a parameter of that method. So just by accident, its name is the same as the depth we had this. But I may hope that it does not confuse too many people. So when the depth is 1 and they try to build the left and the right subtree, of course they will call it with the parameter depth equal to 1 minus 1. Therefore, when they come here, the parameter value will be exactly 0. So this will hold and they will stop. The rest of the condition says if a random value is bigger than 7. What does that mean? That means that not only we just stop, or the function stops when it reaches the last level it is capable to process, but also it can stop sometimes randomly, not just when it processes all the levels, sometimes earlier, just by random chance, asking the random number generator if the current random value, which is just generates for at this very moment, if that value, which is between 0 and 10, is bigger than 7. So a random range generates anything out of the set 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and I suspect that it generates also 10 in Python. I'm not quite sure, but that does not matter. So it generates by some pseudo-random mechanism, it generates some number. That means it points randomly to one of these values and asks if that value is bigger than 7. So if it points to 3, nothing happens. If it points to 9, so then they say, aha, random value at this moment is bigger than 7, so we do stop. This results in the shape of the tree you have here. So that's then we can generate stuff like this, create the tree. Now, what is important when we do this? First of all, note that the function returns the node which it has just created. So it creates the node, asks the same function to create left part and right part of the whole tree. those calls do their job, and when the function returns from these calls, they go immediately to returning new node. So what been just generated is returned. So if you in this example of function call say, okay, create a empty binary tree with no nodes in it. This is just something, the first line is just technicality. What is important that you say, well, now we have an object which is called binary tree. It has a function, a random tree, which of course should be the same. This RND tree should be exactly this one. So there is this error. Those names should be the same. This RND tree should be the same as this one. Let's see how it is on the web page. In our codes. Do we have it on the binary tree? Let's see, open binary. What was that now? They don't have. Now that works. And it does not work. Too complicated. How it's called RND tree. So the name here at the top is random tree. You can see that it is the same stuff as we had on the slides. So back to the slides. Back to our examples. What is important, and when we call the function which generates tree, we have an access only to the only node which it returns a reference to. So our tree or anything like that contains just a reference to the node. We can look there and print out some values or the key which is there, but we don't have a direct access to everything which is in the rest of the tree. So we want to look inside the tree and, for example, print it out or list it, put it into a sequence or anything like that. So we need a method which can traverse the tree. It's a surprisingly new problem. So far, when you have, for example, a list of values, 71, 68, 45, 94, and so on, in a list, you can go through the list in one loop or anything similar to that, and you have an access to each element, or you have an access by an index if you are in an array, or indexed array, or in Python in list it is also possible. So that's not a problem. In a tree, suddenly there's a problem to getting to the leaves. How many leaves are there in your tree? I don't know. So what do we need is a system which can visit all the nodes in some manageable order. And that manageable order is called, for example, Inorder. They have already created this tree which is up there, and when they want to see what is in that tree, they say, okay, we've got this function here which name is Inorder. It has a reference to a node, and then it does some work. What work? First of all, if the reference is completely empty, then the function does nothing, obviously. Otherwise, what do? They call themselves. So again, here is a recursive approach. Look in the left subtree of that of our current node and do the stuff there. Which stuff? Well, with the same stuff which our function does. Then they print what they are looking at, the key in our current node, and then they, after that, they do the job, the same stuff they do in the right subtree of a current node. So that means that they start where they start. They come to this node 13, and before they print the 13, they have to go according to this statement. They have to go left, and when they come left, they are again in this function. Node is still some node, and before they printed at 39, they have to go left again. Listen, node left, what is left? There is 84. When they come to 84, because they call again the same function, they are in a node which is here marked by 84. So what do? They first go to the left. There is a node named 98, and in that node, what do? They call again. They try to go left from 98. When they try to go left from 98, and they call themselves, please do the job in the left subtree of 98. The interpreter, of course, does it. It calls this function with the left child of 98, but that left child is none. It does not exist, and therefore, immediately when you try to go to the left from 98, the code executes this condition, node equals to none, of course, because there is nothing to the left of 98. So it immediately returns, and it returns back to 98. And when they are in 98, the same code, this part called the left subtree, which does not exist, that we already know. And then the next thing they do is just print the key of current node, which is 98. When they print 98, they try to process the right subtree of 98, but that right subtree simply does not exist, so nothing happens in there, and the whole the code returns back to node 84 from where it was called. So as you can see, what is the result is that when we when you take this tree and perform this code, the result, what is printed out is here at the bottom. You can see that the root value is printed in the middle, and to the left are all values which are in the left subtree, and to the right are all values which are in the right subtree. And that holds for any other node. Take 83, for example. So to the right are the values which are in the right subtree of 83, and to the left are two values which are in the left subtree of 83, 58 and 5, 58 and 5. So in order means that you run through all the nodes in the tree, and what you do is that before you print, you look at the node, and before you do anything with it, you first go left. When everything is done on the left, you return back to your current node, and then you do the stuff, print or whatever, and after that you process the right subtree. The picture, it's like some meteorological map with some winds. So this is a atmospheric movement. It isn't. It's a tree processing movement in the tree during in-order traversal. Here, the important part of the code is repeated, and the blue dot. Is simply denoting when the output happens or when processing of a node happens. So when they start, you can see how they move to the left. They try to go to the left of H down there, but there is nothing. This last row represents no node. respectively empty reference. So they try to go left, nothing happens, then they print age, go back, try to go work in right subtree of age, it does not exist, so they return back to D. Aha, they have returned from the left side of D to D, so print D and process the right subtree of D, which is I. So there happens exactly the same thing. I is printed, and when it is printed, the program returns to D. And when it returns there, it is returning from the right subtree, so there is nothing to do, so returns happens, and it was the processing of the subtree with the root D was called from the node with value B, so that is printed, and you can see. So when you go from the left to the right, if you draw your tree in rather stretched manner, and then you let all the nodes drop down, so you can see what you got as an output is exactly the order of the nodes from left to right. So that's the way how to access, how to traverse the whole tree. Visit each node 3 times, because you come to the node and you go to the left, you return to the node, go to the right, return to the node, and then you go to the parent, and you never return to this node back again. So visit each node 3 times. No more than that. It is probably impossible to visit each node only once or something like that. But nevertheless, 3 times is a constant time. So in time which is proportional to the number of nodes in the tree, you can scan or traverse the whole tree visiting each node. All right, so might be happy with this. And because this is not the end, they say, aha, now they are getting just very mechanistic. They say, all right, what if we take exactly the same function we had before, this is completely the same, and only the print statement is not between the left and the right call, between going to the left and going to the right. What if we first, when we come to a node, what if we immediately first process it, that print the value which is inside, and then we process left and right subtree. This approach is called preorder traversal. Pre means that before you do anything else, you process the current node. So you arrive at 13, and immediately when you are in 13, you process it, that is, you print it out. Here is your 13. Then you move to 39, and when you arrive to 39, you immediately print 39. Then you move to 84, and immediately you print it out. 98, you print 98. Now you are in the leftmost part of the tree. There is nothing more to do, so you return back to 84, where it still remains to process the right subtree of 84, and they go to that right subtree, and immediately they come to, for the first time, they come to 71, they immediately print it. Then there is nothing to do down there. Return to 84, nothing to do. Return to 39, nothing more to do, because there's no right subtree of 39. So you return to 13. Well, we already were in the 13. Here is our proof, but we still have to explore the right subtree of 13, and there it works in exactly the same manner as before. 83 is the first node found. So immediately you print out 83, go left 58 and 5, and finally 28 in the end. So the atmospheric picture is still the same, only the position of this blue dot, which says when you process the node, was changed. Immediately when you come to the node for the first time, you print out or you process that node, do whatever job you have to do in that node, and then you continue exploring left and the right subtree, for example, of D, and on the right side, of course, it is still all the time all the same. And you come to a little bit strange output in this case, because look at it, you print A, B, D, H, A, B, D, H, then you print I, then you print E, J, K, and now the whole left part has been processed. They return back to A along this edge, and then they do the same stuff on the right side. That means they could print CFL down there, and so forth. So it is not obviously immediately when you look at this how the tree is arranged. But it does not matter. Now, the third method is, of course, to do the work after you have processed left and right subtree. Its name is Postorder. That means after you have done your work. Means that first you call yourself. That means the function calls itself on the left subtree and then on the right subtree. And when those are processed and completely processed, then only then you go and process your current node, and when you do it, then you return to the parent. So you start in 13, nothing happens. Go to 39, nothing happens. Go to 84, nothing happens. Go to 98, nothing happens. Explore left and the right subtree of 98, but they do not exist. So you return back to 98, and that's the last thing you do. You print it out, and then you return to 84. But being in 84, you haven't explored right subtree, so you explore right subtree which contains 71. That's being printed, return back to 84, then return back to 39. And there is nothing to do on the right, so return back to 13. Still have to explore the right part. The right part, you go down to 83, 58. Nothing happens because this is Postorder. After you do everything below, only then you can do anything on the higher level. So getting down. 5 has no children, so 5 is printed. Return back to 58. Now go to the right subtree of 83, and there is your 28. Return back. Now finally 83 comes out, and as the last, completely last output is value of 13, because 13 is stored in the very root of the tree. So those are 3 methods, very simple ones, how to get to each node of the tree and do some job there, and don't get lost in that complex maze of edges and nodes in a binary tree. Of course, it has to be binary tree. If you have ternary tree, then it is a little bit more complicated. Nevertheless, the approach might be absolutely the same. So maybe we will check ternary trees during the seminars. Now is the next question, which I am going to present at the moment. Let us generate a little bit less random tree. What can we do? I just go there. I just jump there. Maybe am I going to comment this? No, we can do it during the seminars. Those are very simple examples how you can, other ways how to do something with a tree. Count the number of the nodes. Well, how many nodes are there in any tree? Well, ask your left subtree, ask your right subtree how many nodes they do contain, then add 1 for your current node, and return this total of the 3 values to your parent. Maximum depth. How do you assess maximum depth? Well, you are in a node, you don't know the depth to the left and to the right, but you can ask them. You ask your left child, what is their depth? You ask your right child, what is their depth of their subtree? What is the longest path from the leaf to the right child? And then when they refer to this information, then you say, okay, you've got this depth, for example, 17, you've got depth 24, but I am above you, so the maximum depth is then 24 plus 1 because you are my children, you are my child, so 24 plus 1 would be 25. Exactly this happens on the slides. When you are looking for a tree depth, you start in the root there and ask left and right subtree what are their depths, and you do it exactly this way. Take the on the left, take the depth on the right, take the maximum of those at 1, and return that value. Very easy. But what I want to show now is processing a tree which is a little bit more regular, and they want to do it just because they want to introduce the stack for processing the trees without recursion, which typically sometimes might help, so we have to go into it maybe a little bit more quickly, but that I hope does not matter. Okay, so what do they want to print? They want to print the sequence which is here in white, highlighted, and you can see how it is created. It has some length, and the central, the middle element is the biggest one. Then you divide it to the left and the right side to that biggest element. And in that part, you, again, in the middle of that part, you put there the maximum value, but that maximum value is smaller by 1 than the previous value. So the scheme above the numbers just shows the magnitude of those numbers, so you can see how it is structured. And the smallest value you can create is 1. So if, for example, if you want to have also 5, then what would you do is you would take exactly this whole part, copy it once more to the right, and in between you would just put value 5. So you create just this sequence. How can you create it? Well, there is your code, which now we know that it is an in-order processing, because first it's not seen there, but we will see it in a moment. You as if call the function once and call it for the second time, and in between those calls you process something which is your current value, and that means you print it. Again, you decrease the value when you call the same function recursively, and of course you stop your recursion when value is too small. You don't do anything. So this call ruler 4 produces exactly this output which is up there. Now they here want to stress that the function which produces still the same output has the same structure, identical structure as Inorder traversal. So although we do not see it, there is in fact a tree hidden when we make a recursive function where we process something, then we do the stuff, and then we again process something else, and that something else is processed by the same function. There are 2 calls, and you can imagine that you go to the left and you can go to the right, and in between you do some stuff at your current level, and then you move to the lower levels with those recursive calls. So this is important that areas are structurally identical, and this is a method which we have seen list in order, which processes some tree. So you can expect that in fact here is hidden some tree. It is there. It's a tree of recursion of recursive calls of the function ruler, and you might imagine something like this. Again, if you start printing. So what you do, process left part, process right part, and in the middle you print 4. How do you process left part? Well, how do you go to the left and what? And now the value is smaller by 1. You started with 4. So now you take value minus 3. What you this value 4. You put there 3. Therefore, when you arrive to this point, the value is equal to 3, and therefore your recursive calls have again 3 minus 1, which is 2, and again here it continues in the same fashion. So in fact, what happens that you can think of the whole work which is done during a recursive call like this as a tree structure, which simply produces, in this case, it produces some output, and it also traverses some tree which is in fact which does not exist. It is not in the computer whatsoever. But you can imagine that there is some abstract tree, and the computer is moving along its edges up and down by these recursive calls. So having this, the next step is rather difficult. This is my most dreaded picture in the whole presentation. I can never remember what does it mean. It is trying to show you how the function, which was on the previous slide, how the function progresses. It comes to a node that is it is just called, it calls itself, so it is something as a coming to a node of a tree. Then it calls itself 2 times, and again you imagine that as processing left and right subtree of part of the current call. And what does it does that it goes and processes left subtree and returns back. Then it processes right subtree and returns back, and after that it returns to the previous, to the call from the higher level, and in between sometimes it processes, here it does something. So so this is this detail which is expanded on the whole slide, and the numbers on the edges in relation to this particular node tell us how many times A was visited. So the function comes in, A was not visited, so there are zeros. Then it goes and works in the left subtree, and A knows it was visited once. Then function returns back to A and goes processing right subtree, and then the node A knows, they have been visited twice. First time when they came from the top and from the parent, and then after processing the left subtree, they return back to A. And now when the function works in this subtree, A knows that it was visited twice, and when this is done, right subtree, then the function returns to A for the 3rd time and leaves it in the direction of the parent. So A was visited 3 times, and that means the function call never returns to the same point again. So that's the meaning of the picture, more or less. And now you say, all right, let us do the same without the recursive call. Now here they try to be somehow clever. Let us try to do the same. So we create the stack. We will see the stack in a moment, how it operates. So I just try to go through the description, and that should be short because the example should help us much more than just the text. Push the first node to the stack, first element to be processed, and it is typically the root of the tree. Each next node, each next element to be processed to the stack to So you move down the tree and push the nodes on the stack, so your stack grows and grows, all right? Process only the node at the top of the stack. We'll see how that works. and pop the processed element from the stack. So when we finish, we will see that in action. The last rule is very important. When the stack is empty, we stop. So to process a tree, we have to first take the first node, put it on the stack, which is originally empty, then do the stuff which is described on the next 3 lines. And when the stack becomes empty, the work is done. You don't have any other checks. You're just keeping track on your, keeping an eye on your stack. And whenever it suddenly there's nothing to say, everything is done. So let us see how that works. We have that tree of function calls only partially. You can imagine that on the right side there is the same picture as here. And when the function starts, it goes and first it has to print, it first goes to the left, and after everything it just processes that for. What do? You take your value, which is that value which has to be printed out that for, and put it on the stack, and also you put on the stack how many visits were in this particular node where we start, which is the root. So you say you push the value 4 and number of visits is 0. Now, as we are moving down the tree, a function is calling the function with smaller parameter 3. What happens is this. The call has moved to the next node, where they do exactly the same stuff. You take now the previous value 4, decrease it by 1, because we are going down in the tree, decrease by 1, and say, okay, we have visited this node 0 times. And as you can see, also this number of visits in node 4 has been increased by 1, because when we left 4 going to the 3, we already know that here we have exactly 1 visit. And now we are descending through the tree down, and the information about the descent is being stored in the stack, like this one, moving down, coming to 2, and when we are leaving 2 and coming to 1. Again, it is pushed on the stack. You can see that the number of visits in the previous nodes is already set to 1. So we go down until we go past this node. That is, we have to call the function with parameter 0, and if you remember, unfortunately there was probably not enough space to squeeze it on the slide. They say when the parameter is 0, you don't do anything, you just return. So you say, aha, so there is 0, so you push it on the stack. What happens next? You immediately just remove it from the stack, and that is your top of the stack is now. Here you have returned to node number 1, and now you look and say, we have visited this node 1 time. So now we are there for the 2nd time. This is number of visits. We are currently here. So so now we are here for the 2nd time. It is time to print exactly this value. Which suddenly appears here, and now they indicated they have been in this node 2 times. And go to the right, that means you push down a smaller value on the stack. We have been there 0 times, but unfortunately there is nothing. So immediately what follows is just removing that value from the stack and returning back to 1. Now we are in 1. How many visits? 2 visits. So there is nothing more to do. Return 1 step up. Excuse me, we are now here. 1 was visited twice, so we move up, and that means when we go from 1 to 2, returning from 1 to 2, coming to 2, we are in 2, and we were there once, so we are coming for the 2nd time. That means we are going to print the value of 2, increase the number of visits in 2, and go down. And again go down. And now the process work in this same manner. You can see that what is on the stack is one path from the very top to maybe sometimes to some bottom or to some node, maybe a little bit more higher. But what is stored there is just one sequence from top to some node, and you just remember how many times you were in each node which is on that path, and you are trying to go forward. If you cannot go forward, you return back. See how many times you visited the particular node. If there is still something to do, you again try to increase your stack and move downwards in the tree. If not, then you move again, shorten your stack and go back, up in the tree. So that is exactly what happens there when everything was processed. Here now your stack is becoming very short. You do the same stuff here in 3, print the 3 and increase this value, and so on and so on and so on, as they say here. And after a while you arrive at the final configuration when everything also in the right subtree, which is not shown here, was processed. Then 4 has been visited 2 times, and now when it was visited 2 times, we remove that information from the stack, and now stack becomes empty, and the whole process is stopped, and our output is here. So that means, and now it's becoming a little bit more terrible. I will spend 5 minutes commenting this. Now you can see yourself. This is the code which reflects the stuff with the aerobics which we did with the stack just now. Now I repeat it once more. And the code is this long. Now I go back and remind you what the original recursive function looked like. It was this. So the effect of this function, which prints out such output, is the same as the effect of the function which does not use recursion and implement stack, and you have to keep the track of the stack. What's on the stack reacts to each situation on the stack and behave accordingly, and that is done in the code which does all of this, and the code is here, and there are all those cases which we have seen so far. So you process while stack is not empty, while you are moving up and down in the tree. There either you, what you do, if you see that the value is 0, that means we have come to the very bottom of the tree, you just pop the stack because there's nothing to do. And then there are 3 cases according to the number of visits. Either the number of visits is 0 in current node, either the number of visits is 1, or it is 2. If number of visits is 1, you can see that here is the print statement. It is this case when we it is this case. In this case, when we get, for example, to 3, there is number of visits is 1. So you say, aha, it's time to print 3 down there, as they have just done. This is that part, and the rest should be more or less obvious. If the number of visits is 0, then we increase that number of visits, and we store on the stack. The name of storing on the stack is push. What we do is push at the stack top. We store there value, the previous value, 4, 3, 2, 1. So you decrease that value by 1 and store that with 0, telling them that we are moving down, and in the next node to which we are currently coming, there we have zero visits so far. If we, on the other hand, come to the node for the first time, the number of its visits is 0. Then we just increase the number of visits, and then we again push exactly do the same stuff. You can see that this line and this line is exactly the same. And when the right sub-tree is processed, that it means that we had 2 visits. So in that case, we just pop the stack. That means we shorten that stack. And that's it. So, and you can see that it's much easier to make a mistake here than in the previous recursive call. On the other hand, there is one single advantage of this approach. You are not dependent on the number of function calls. So if you have a recursive solution, recursive and non-recursive, recursive. Of course, if your solution is recursive, solution recursive. If it is recursive, then there are many function calls stacked somewhere, because you go the call function, again call function, call function, call function, and so on, and then you return back. You are limited by the size of the system stack, because when your machine is executing the code, it has to remember somewhere all the sequence of the calls which you have made so far, as in this picture. This represents one call, another call, nested calls, and because they of course have to return from those recursive calls, they have to remember all those previous calls, and those are stored on a system stack in the fashion which is very similar to this which I present on this abstract example. So that system stack is limited. So if you want to store 50,000, or maybe now I am making this up, but very surely, if you make a 50,000 nested recursive calls, you'll get an exception. Your program typically crashes because the system says, okay, well, we cannot handle this program. We don't have enough space on our system stack, and you cannot influence that anyhow. So if you expect extremely many nested recursive calls, then it is time to go into a variant which has no recursion in it. You can see that the only additional data structure we are using is the stack itself, but as you can see, it is just a list or an array. So typically there is a lot of space for storing some 50,000, 100,000, 70 million value in the memory. So we are much less limited when you go non-recursive. So this also let's say unlimited by the system stack. limited. So that's why we have this non-recursive approach. And of course, it helps us understand what's going on when we do our recursive calls. So there it is once more with the arrays. Doesn't matter, this code is once more presented here with arrays, so it is even much more terrible, even closer to the machine. So I leave it there for everybody to check themselves whether it works or not. Then the same code is there for the third time. All those else and else if cases are somehow merged together, so you can get shorter code, but it's very difficult to debug if you make a trivial mistake there. Plus, you can see plus minus one. You just forget one plus or minus sign, and your code simply, of course, will not be working. So I do not recommend too much this to do this. So that it is, and in the remaining few minutes, I have to mention the backtrack. We will return to backtrack very probably in some of the next week or the week after that. So I will just give you the very simple introduction. The problem is a well-known introductory computer science problem, your typical sandbox programming problem. How can you put 8 queens on a standard 8x8 chessboard so that none of those queens threatens any other queen? So here you can see examples when they are sitting. Each of those queens is sitting in its own row. It is sitting in its own column. So there is one in each row and one in each column, and also their diagonals. Each is occupying 2 diagonals, and those no two queens occupy the same diagonal. So there are some solutions, and then we can go and say, okay, and what does it have to do with the trees? Well, if you think about it, what you do when you try to solve such a problem, you can say, okay, so let us start at the very beginning, brute force approach. Try to put your queen in the leftmost corner in the first row. Okay, that's one possibility. You can have queen there and try to put there other queens. There is the other possibility. Take your queen and do not put it in the first column of the first line, but to put it in the second column of the first row. And then you can also try to put it in the third, fourth, fifth, seventh, and the 8th column. So there are 8 possibilities, and each of those possibilities again can be expanded by trying to putting a queen on the next row into some positions. As you can see here, they just show you that when the queen is in the corner, so then you can put in the second row, you can put a queen, for example, there, and then there are just left only few free cells on the second row where you can possibly put your next queen, because all other are already threatened by the queens which are already on the chessboard. And that happens for each configuration you can imagine. Therefore, what you got is in fact a tree. This is a tree. It is not binary tree. It has at most 8 each node. Each configuration has at most 8 children, but that number of children, as you can see, is reduced relatively quickly in the deeper levels. So what you do is you in fact have a recursive function which goes through the tree of all possible configurations, and in each level you consider only the upper part of the of the configuration. So it looks, for example, a little bit lower. It looks like this. Again, when you've got this configuration, then you have 3 possible. This cannot be sitting there. So you put, this one is, you put your next queen here, and that can be expanded in only 2 ways. You can put your queen on the position to which I am pointing. Now it's there, and suddenly there is only one possibility where to put the queen on the 4th row, and there in the 5th row there are again still some possibilities. So it's a rather big-ish tree. I don't know how many possibilities are there. So this is another part of the tree. You should imagine that the previous slides are somewhere else, and some are farther up on the wall. And there you come to a situation when you can see, everything is already occupied. You have only 2 columns unoccupied, but they are the free, these free spaces are still threatened diagonally by some other queen up there. So there you stop calling your function, and you go back. So there is some small comparisons which I will talk about later. How effective is your brute force, which would just generate everything. Our backtrack method is a little bit better. They find some number of solution which is not so difficult. And the last part is the implementation, which probably we will again do not, and I will not comment it now, because that would take another 5 minutes. As you can see, the whole function is relatively simple. Its name is putQueen, and it is called recursively in some column. And what is always important when you are in a particular row, so you call recursively the same function on the next row, as we have seen in the examples here. When you are in this row, where the blue circle is, then you try to process the configuration with on the next row. And so on. So that's just for very quickly this stuff, and we can maybe discuss it during the seminaries, because now I am overdue more than 4 minutes. So thank you for your attention very much, and we will have our seminars, our practices in, I presume it's number 340 is our next classroom. So thank you very much, and see you there.